A jewel in the crown of the city of joy, the Metro Rail in India began its journey in Kolkata on October 24, 1984. But Kolkata, a city in need of renewal, is in dire need to provide its citizens the best amenities available in the country. Working towards achieving the goal, one of the initiatives taken is the East-West Metro Corridor, connecting Salt Lake City to Howrah Maidan, bisecting the existing North-South line at Central Station, which would be the interchange station. A complex challenge taken up for the first time in the country by Kolkata Metro Rail Corporation Limited. A journey whose end is in sight. A journey which will give Kolkata its second metro. A metro the residents would be proud of. With 6 stations underground and 6 elevated stations for the entire stretch, the design and build contract of the 5.263 kilometer underground twin tunneling with 13 cross passages from Central Station to Subhas Sarovar, including the 3 underground stations of Centrals, Sialda, Phoolbagan, a crossover, and the ramp connecting the underground tunnel to the elevated viaduct, worth Rs 9,086.31 million, was awarded to the joint venture ITD Cementation JV. ITD Cementation JV has been a constant partner in the growth story of India. The joint venture company has considerable human resource commensurate with the expertise required and possesses all major equipments for successful execution of the projects they undertake. The JV has built many iconic projects. Notable amongst them are Kolkata Airport Integrated Passenger Terminal, elevated viaduct and underground tunnels and stations at Delhi Metro, BC21 and BC24, Talha to Palta pipeline at Kolkata. Over the years, ITD Cementation JV has developed expertise in design and construction of large infrastructure projects. Along with the Kolkata East-West Metro tunnels and underground stations, the JV is also executing the underground stations and tunnel for Delhi Metro CC32 package. The entire project is executed in 5 steps: geotechnical analysis, designing, mobilization, implementation, and restoration. First, the locations of boreholes are laid. Based on the location, pits are excavated to probe for underground obstructions or utilities. Then the holes are bored with a diameter of 150 mm and up to a depth of 30 meters as per the specifications laid in IS 1892. Standard penetration tests are conducted to calculate the load-bearing capacity of the soil at site. The groundwater table is analyzed. Based on reports and analysis, the design for the entire project, with a design life of 120 years, is completed and the construction methodology is defined. The next step is to set up the sites of operation. Once the sites are acquired, the obstructions and utilities are bypassed temporarily for site operations to proceed without hindrance. The traffic and pedestrian movements are bypassed. The site is mobilized for operation and all required logistics are put in place. To commence the first tunneling drive from Subhas Sarovar site, the cut and cover methodology is adopted. First, a guide wall is constructed to define the exact layout of the diaphragm wall, commonly known as D-wall. Excavation for each D-wall panel is done using a hydraulic rig to a depth which depends on design requirements. During the excavation in grab operation, while the excavated soil is progressively removed from the trench by grab and loaded into the disposal area, bentonite slurry is continuously supplied to maintain slurry level for trench stability. The stop ends are lowered. The reinforcement cage fabricated on the ground is lowered using cranes, maintaining the vertical alignment. The couplers are fitted to be left open to join with slab rebars at a later stage. Concrete is poured through tremie pipes. The process is repeated in panel sets to create an interlocking D-wall along the guide wall alignment. Excavations for slabs are done within the D-wall zone. On reaching a certain depth, the first slab, called the roof slab, is constructed with temporary openings for access. The rebars of the slab are coupled to the couplers of the D-wall, left open previously. Small size excavators are used for excavation below the roof slab. As more depth is obtained, temporary structural supports are provided to counter the soil load on D-wall. The base slab is constructed similarly as per the requirement of the site. Excavation and construction of the ramp side is completed. To create the elevated viaduct, piles are constructed by boring holes, placing the rebar cage and pouring concrete. Pile cap is created and then piers are constructed over the pile cap. Pier constructions of different heights are done to extend the ramp above the ground to the desired height. The ramp is connected to the elevated viaduct constructed by other contractors. Precast parapet walls and railings are laid to complete the construction process for the elevated portion. Shear connectors are left open as per requirement. The tunneling operation begins with the setting up of the state-of-the-art high-precision tunnel boring machine, commonly known as TBM. The 100-ton gantry crane is set up. A total area of 14,000 square meters is used to set up the backup logistics. The front portion of the TBM with front shield, middle shield and cutter head is lowered on the steel cradle using the gantry. TBM backup units like erector, screw conveyor and tail skin are lowered and commissioned. Once ready, the TBM is launched. The soft tie of the D-wall panel, which faces the cutter head of TBM, is made of glass reinforced fiber polymer known as GRFP. This provides strength but can be cut easily. With its rotating cutting wheel, the tunneling machine cuts through the panel and excavates the soil. The soil is conditioned with water, bentonite, stabilizer or foam using the injection systems located in the backup. The soil is then retained in a mixing chamber to maintain the earth phase and water pressure balance. While the hydraulic cylinders press the machine forward continuously, the sensors maintain and map the earth pressure balance continuously as excavation proceeds. Via a screw conveyor, the soil is then moved to the belt conveyor system in the rear of the shield. The screw conveyor's rotation speed is matched to the advanced speed. The rail lines are laid for the movement of mud trolley car and segments transportation. Soil excavated is moved out in trolley cars, which are pulled out by the 35-ton gantry cranes. Concrete lining segments are casted in the casting yard and brought to the tunneling site. These cranes are also used to lower the concrete lining segments in the shaft. At main drive, the tunneling speed is 12 to 15 meters per day. The reinforced concrete segments, known as lining segments, are installed using the erectors. When the ring building has been completed, the machine can push itself against the new tunnel ring and draw further into the soil. The 80-meter-long backup accommodates all the logistic facilities necessary for the operation of the overall system. While the tunneling proceeds, continuous monitoring using advanced monitoring instruments is done on subsurface infrastructure, including residential and commercial buildings, to check the surface settlement of soil. The second tunnel begins with approximately 1 month of gap. Both the tunnel boring proceeds together in synchronization. Starting at the Subhas Sarovar end, the tunnel breakthroughs on the other end at the Phulbagan station. The site is first set up and D-wall is constructed towards the breakthrough end. A temporary D-wall is also created to create the zone for TBM breakthrough. The excavation completed, the slabs are constructed and the receiving shaft is completed 1 month in advance prior to TBM arrival. As the TBMs break through, they are removed through the receiving shaft using the 100-ton gantry crane. They are then sent to the Sialdah crossover for the initiation of the next tunnel as per scheme. The backup logistics from Subhas Sarovar is demobilized and set up at Sialdah crossover. At the crossover, the site is prepared, excavation completed and slabs are created. The gantry crane is erected. The initial drive is launched with the backup logistics set up on the surface. While tunneling in initial driving mode, power will be connected from the power units situated outside the tunnel to the shield machine via hoses and cables. The soil is excavated and removed by a bucket and crane and progresses at the speed of 3 to 4.5 meters per day. In this case, the cutter head and front shield extends for 80 meters at first stage, creating space for the TBM backup to be lowered. Once the TBM backup logistics are commissioned, the main drive is launched, cutting through the entire tunnel to the Phulbagan breakthrough. The conversion from initial to main drive takes 3 weeks. The tunneling process is repeated now from the crossover to the Sialdah station, and then from Sialdah station to the central. Then drilling and grouting is done with self-drilling anchor machine for roof support to prevent collapse of soil while excavation. Temporary bracings are provided as support on both the tunnels. The concrete segment face is removed. Earth is excavated. Wire mesh and shotcrete is done, and structural support is provided using beams. Finally, the inner RCC lining is constructed to complete the cross passage. All supports are then removed. On completion of all the tunneling activity, track bed concreting is done using PCC, and shear connectors are left open for laying off tracks. Walkways are installed. For the stations which are being constructed in parallel, a top-down construction methodology is adopted. Excavation is completed and slabs, roof, concourse and base slab are constructed with permanent and temporary openings as per requirements. This creates the underground box structure for the station. The platform slab is constructed. Then follows the secondary structures, the permanent columns, staircases, lift wall, office rooms, architectural, E&M and plumbing works completed. The interfacing agencies are provided access to complete the tasks in parallel. Finally, all temporary openings are closed and final reinstatements are completed. All utilities are restored before the handover. The completion of 5.263 km tunnel with 3 underground stations, 1 crossover and ramp is high precision engineering on which depends the daily life and business of the entire city.